Almost everything that we got retrieved had to be filtered out. Think about it. If there's a lot of things that you can get the database to do, then the applications become simpler. I was an engineer at Instacart. I mainly worked on the Postgres storage infra search team. I would say it was almost a silver bullet, but not quite.
Hi, this is Benjamin. Before we jump into the show, I wanted to quickly reach out on a personal note. We've just launched Firebolt Core. Firebolt Core is the free, self-hosted version of our Postgres-compliant SQL query engine. Firebolt Core runs anywhere. You can run it on your laptop, you can run it in a scale-out configuration on your local on-prem data center or public cloud environments. Firebolt Core is great for either running big data ELT jobs on, for example, your Iceberg tables, or powering low-latency customer-facing analytics on big data. We'd love for you to try out Core and give us feedback. You can either hop onto the GitHub discussions or issues, kind of join our Discord, or just send me an email at benjamin@firebolt.io. We added a link to our GitHub repository to the show notes. And with that, let's jump straight into today's episode.
The Data Engineering Show is brought to you by Firebolt, the cloud data warehouse for AI apps and low-latency analytics. Get your free credits and start your trial at firebolt.io.
Hi, everyone, and welcome back to the Data Engineering Show. Today, we're super happy to have Ankit on. Ankit is, now a software engineer at ParadeDB, I think, but before that, was a senior engineer at Instacart, did a lot of work on Postgres there, kind of their data stack. Excited to have you on the show. Do you quickly want to introduce yourself? Yeah, kind of share your background.
Yeah, thanks. Honored to be here. So as of 2 weeks ago, I was an engineer at Instacart. Now I've just recently moved. I mainly worked on the Postgres storage infra search infra team, and there's a series of blog posts on how the search was modernized that will more talk in detail today. Search was modernized with hybrid retrieval, and there's also talk of how we moved from Elasticsearch to Postgres, and we'll talk about the reasons later. Before that, I had worked in a bunch of different startups in Canada and India as well, and had always been interested in databases, and special love for Postgres because in my experience, choice of database boosted dev productivity in general. Think about it. If there's a lot of things that you can get the database to do, then the applications become simpler. And my non-Instacart experience has largely been in, I think it's a pre-PMF startups where the approach of abuse your database to its absolute limits, it works wonders. Now, you can argue that it can be done at scale too, but that's for later.
Nice. So take us through search at Instacart, right? And I think one thing that also is interesting to our listeners is and it was similar for me as well for a long time, you have in your mind, okay, here's my traditional relational SQL database. Then there's search things. And I think traditional, there would actually be little overlap between these things. And I think what you're seeing nowadays, and I think Gen AI is actually also driving that even harder, is you see this kind of merging of these concepts into individual system that can do everything. So kind of maybe take us through how do these problems actually pop up in the Instacart product, and then how did the tech look?
Yeah, that makes sense. Let's go one step back. Let's talk about retrieval in general. What is the lay of the land of the retrieval? What was the lay of the land? So there is if you go to Instacart app as a consumer, now again, there's different apps for shoppers, there's consumer, and then there's ads where brands do their thing as well. So I'm sure there are retrievals over there as well. But as a consumer, the first thing that you get in touch is auto-suggest retrieval. So you type BAN and you expect banana to be there and bunch of banana smoothie and whatever is there in the grocery store. So that's one retrieval. Then there is, we call it home search, which means you just say, I want eggs, and the app would show you a list of retailers and bunch of items in each retailer. That's one retrieval. And then there's another retrieval, which is, which grocery store you care about because you're very passionate about, I want my eggs from this specific. And that's me. My eggs come from one grocery store.
I know the chicken. I know the mother of the chicken who raised her, and she has great eggs.
Right. So that's how it goes. So that's the single retailer search. And that's the biggest, you can say, search retrieval by volume and by sort of strategic importance as well. Instacart is a retailer first marketplace compared to the peers. And this blog only talks about this line. We don't talk about anything, even auto-suggest. And you can imagine a bunch of other retrievals exist that I don't even know. I'm sure some teams are still using Elasticsearch for their underlying retrieval, like Ads Manager. I have never even seen that. So it would have some boxes for search. Someone team was also using ClickHouse via a foreign data wrapper in Postgres because it works for them. So why not? One flag that I get after the blog was released by Elasticsearch fans is that they felt that the blog claims that we kicked Elasticsearch out of Instacart. No, that's not true. We only removed it for the third kind, which is single retailer search, and there were reasons for it. And so let's deep dive into single retailer search. So previously we had an Elasticsearch that was doing the search retrieval, and the other things was application. So what are the other things? Filtering the retrieval for some use cases, ranking, and hydrating the whatever was retrieved with more attributes, and then a ranking after hydrating as well. So a bunch of different steps, and it's a standard model, if you imagine, and that's what everyone does if you have multiple kinds of filtering and ranking. Now, what different Instacart was that our items was so fast moving. It's a grocery store. Things go in and out of stock very frequently. And we also have people who care differently about different things. Like I might care very specific about this brand I care about. Someone would care, I just care about getting eggs at the point. I just care about ice cream. I just want an ice cream right now. So different. So you can imagine the solution we were moving towards was an ensemble of models, and the weights of those models being controlled by the context. The context can be the search query, understanding of search query. Now these days is that some of the context is enriched by LLMs as well. Now what we saw, because of the fast-moving nature of the grocery store, like things going in and out of availability, in pathological cases, almost everything that we got retrieved had to be filtered out. So we'd go back to Elasticsearch again. Hey, give us 200 more results or whatever, X number of more results. You do that 5 times. Now, this could happen because we get updates from retailer that, hey, this item is out of stock right now. Or our machine learning models tell us that, the item is gone. For an application engineer, think about it. This situation is exactly what you would see if you by mistake do an N+1 query, right? You have to fire multiple queries. So what's the solution? Well, the solution is to avoid going back and forth across the network where the network delay eats up all your latency. So we created a cluster that had everything in it. It had search index, it had ranking and boosting tables, it had availability, machine learning availability, and all other filter tables that the query may care about. And also we could add more ranking and boostings as the team wanted. And that's what the Postgres was too. In a sense, we traded off the quality of retrieval, hardcore core retrieval, with the whole system reducing the network calls. So I guess another way is to say that we pushed down the compute to the data layer, closer to the data layer, which is I guess an approach opposite to what you guys are more familiar about. There's a very different world where separating the compute and
we love pushing compute to the data layer. Like we're building
By the way, the beauty about our
yeah.
space, it's confused. There's a lot of confusion. Like you said something now, pushing down the compute to the storage. We can even go further and say, to get the speeds we need to offload a lot of the compute from reading to writing.
right.
It goes into pruning, even into the codecs you apply on your data. Like what we say, you push compute down to the storage is actually, in many cases, 80% of what gets you from A to B and gets you to production.
Awesome.
And yes, this is all hidden, done by engineers. Go on.
Right.
So you came to the realization where, okay, we need to do that. So what did you do?
Yeah. So we traded off the Elasticsearch like BM25 with a TS vector, and there's some modifications had to be made to how the TS vector is queried. But essentially, this gave us avoiding of the pathological cases. And there were side benefits also, like, data stored in normalized tables was cheaper than full-blown denormalized. And also there's operational benefits and simplification of stack, like the infra engineers, which is like sort of my team. We were not owning, operating, and managing two different systems. It was just the application would call single query that does a lot, and we'd get done with it. Also, one thing which we missed out writing in the blog is that the cluster is not just a search cluster. So search is one of the workloads it's offering right now. It is a place to go to find what item is available, where, in what store, what item is available, at what price, including full product taxonomy graph and product and ontology. So you could query products, filter, rank them in any sort of flexible way you want in a single query.
Yeah, so maybe one or two questions just for kind of like me to also understand better the flow. So there's this big Postgres cluster kind of running. It can do a million different things. It can also do search and ranking. Now I go into my Instacart app and I start looking for, okay, let's stick with your eggs example. It's like, how does the request flow actually look here? Like, do you really send a query for every character I type, or you predict what character, like how, like a single interaction with the app of like looking up a certain term, how many queries does this actually kind of cause on the back end?
Right. That's a very good question. So the single character goes to the search auto suggest service, which is a completely independent thing. It's still using Elasticsearch. It has always used, and we didn't change it. It was working beautifully. It does what it's supposed to do. So that's the first thing.
You got a lot of hate from Elastic fans. Like when you sprinkle in a lot of love for Elastic. Like
I mean, it's good. It's very stable, and it does what it's supposed to do. So there is like, my intention was never to say that, hey, this is bad, this is good. It was like, hey, this data model and this whole system doesn't work for that use case.
Right.
And it's
so
generally,
basically you're saying if it worked for spell checking, it shouldn't necessarily work for anything else. And it's good that it still does spell checking and kind of searching, that aspect of searching really well. So all good.
all
And
good.
no
Yes.
disrespect to anyone.
And I'm sure we are doing more than that. We're doing some like, if it's a brand search, and because I do remember there was a time when we were running a Red Bull campaign, and someone would type red, the red bell pepper would be at the top, because guess what? The CTR boosting, the click-through rates of red bell pepper, there are so many people who buy it day to day that they were making at the top. So all that auto-suggest, it still would give you the nod.
So
Top K, Benjamin, top K problem.
Yeah, auto-suggestion doesn't go into kind of your service. So at what point, right, like again, like maybe take me just through the user flow, would my interaction starts sending queries against your system?
As soon as you press enter, that you choose your search term, at that time, the application would construct a SQL query for Postgres, and it directly hits Postgres. There's no memcache, there's no other caching systems. It directly hits the cluster. The application would do certain things like query, we call it query understanding, to sort of build more parameters for the search query to the Postgres engine. And then when we get the response from the Postgres query, it is ranked again by the application. So we have like different passes of ranking. The first pass ranking is done by the Postgres itself. The second one, and the division is just because whatever we want to move fast, whatever application engineers feel that, hey, this is where we want to iterate, it's better to keep that in application and not push down to the database. And that's it. Now, it sounds simple from the architecture side, but each component of it has its own like complexity. I don't think I'm even aware of what that complexity happens. So I can talk more from the architecture, from the data flow side. But the data flow is very simple.
Because you're using Postgres. This is why it's complicated. Yeah, go on.
Right. And but the flow is very simple. The application prepares query, sends it to Postgres, gets the result, and then there's some hydration that final clients also do. By clients, I mean the actual mobile apps or the web application that also is hitting the same Postgres.
Gotcha. And so, I mean, this wasn't vanilla Postgres in the sense that you had like use Postgres extensions there as well, right? Like you use something like PG Vector. Kind of take us through your modding modding Postgres kind of journey? Like, what extensions did you use? Did you custom build any extensions? Yeah.
Yeah, that's a good question. So the shape of the Postgres changed throughout the years. So the large theme here is having control over our own Postgres. So that's the only reason why this was self-hosted. It's a self-hosted Postgres. It uses a very new proxy called PGCat. PGCat has moved on, and now there's a PGDog as well. The same author. It's pretty good. It's stable. It works.
Would you recommend PGCat or PGDog these days?
So I have not used PGDog at scale, but I've played around with it, and I like it. There's a conditions apply, like try it at scale. There could be bugs, but the devs are like, I know like Lev is a friend, and he's very responsive. So, and what it allows is work with a sharded database in a way as if it was not sharded. So it adds the sharding layer to the PG bouncer. So coming back to the question, what the grand theme of here is that we wanted more control over the cluster, how to spin it off, what kind of disks it would have. So that cluster is purely NVMe based. We don't use any network attached. We are okay if the primary goes down for an hour. We would rebuild it back from the backup instead of failing over. Like I didn't want to be on call for that if the Postgres had to be failover. So all the intelligence here that handles the failover in a way is an application. Like even if a replica goes down, you need to blacklist that replica. All that is happening on the application. So you can imagine that the client for the application is a thick client. It does a lot more than just the query. It does all the failover, high availability. So that allows us to be simple on our infra side.
How does data flow into this Postgres database in the first place, right? Like, does it attach to Kafka? Is it just plain updates and deletes kind of being run all of the time? Kind of take us through the entire journey, basically.
That's a very good question. It's a first-class citizen of how this cluster operates. So all the writes are pipelined. We don't use Kafka. The interface is S3. So we tell teams, whoever want to have their data in this cluster, create an S3 home, create either a bucket or a home, whatever they want to do, and tell us that. We would sync ourselves. So we'd poll S3 for changes and get the data in bulk, and all the writes to the Postgres would happen like a bulk write. So like it's either 16,000 rows or 32,000 rows, whatever that is.
So it's append only, or there were updates and deletes as well?
It is merge. Like the Postgres has merge commands. So it would, so we would tell teams to tell us what are the primary keys or what are the keys that would help us identify if it is a insert or an update. And there was no real-time writes or update allows that. We also supported deletes through a very special mechanism. It was you just configure that these rows are supposed to be deleted, and we would do it at a cleanup at a later stage. A big part of the system was also PG repack. So PG repack is something that is like a super vacuum or something. It does it very fast, although it uses a lot of IOPS and it uses a lot of system resources to do that. It essentially creates a copy of your table, real-time syncs it, and at the opportunity it finds, it hot swaps it, deletes the old. So the new table that you get is defragged, it's nicely packed, it's clustered again. So Postgres has this cluster table. Cluster is an overloaded term. I hate that. It causes so much confusion. But what we get is a nicely clustered table that has its rows tied in a way that helps query at the read time, essentially. We were running like tons of repack on, like almost always there is some repack running on. And it was hard, like it was tuned heavily, because what we found is that the read throughput, we can throw more data if the tables are repacked nicely. If they're already fragmented and they're not clustered, the writes would slow down. It's more of a write throughput optimization, and it's probably an order of magnitude more if by the repack tuning. So that's how the writes are going in. And from the customization, we had in the past a custom extension for a dot product. So we were doing one of the rankings we were doing in the Postgres was personalization ranking as well. So you would get your products, and at the end, the final ranking would be personalized. So this was happening in the Postgres through a very, like it's a 50-line extension in C, just to a dot product and read and give it back to Postgres. Now that was all deprecated because pgvector came somewhere in 2023, and we moved our the retrieval to pgvector, but also pgvector could do your own default dot product. I don't think there was any other custom extension that we supported. Yeah,
it's always interesting to hear like these production stories from Postgres. Really, like the amount of moving pieces and extensions being used is really kind of cool.
The interesting thing is you see more and more, you hear about more and more workloads, use cases where when engineers say simplicity, they mean like we want the Postgres interface. We want to be able to normalize. We want to be able to have more complex queries running. There are many moving parts. It's not just a on the metal time series, real time, single denormalized, 5 seconds kind of query span. Like this is something completely different, up to the point where some of the data is being batch processed on the side and hot swap because you need it to be super hot. The data, as it's being served to those users, it needs to be super hot. SSDs were mentioned. Like you can trick your way around it, but then you need to deal with Postgres backend, which is at a whole different place. So you need to have mods, extensions, which gives you exactly the flexibility you need as an engineer to take the concept, the kind of the strength of Postgres and evolve it over time. As you said, like types change, search patterns change. Absolutely. I love it.
Yeah.
Thank you for sharing with us kind of the whole thing end to end, and specifically kind of the whole effort you guys are putting on the back end on.
Yeah, I
it's
would
very
say
impressive.
it was almost a silver bullet, but not quite. There were certain trade-offs as well. Like eventually what we found out was that the DevX, the developer experience and how engineers use it, especially search engine engineers, it was less than ideal, because you realize that most engineers who want to work on search, they are more used to the Elasticsearch shape of the query. And even those who knew Postgres, among those, they found the final query to be hard to work with. And scaling, provisioning, sharding, operating this self-hosted Postgres in a company that relies on managed cloud for everything else. Like everything else is on RDS. It's amazing, right? That was, again, a hard thing. So you have this small team that does its own thing that no one understands. And we also noticed that replicating production behavior in a non-production, it was impossible. So if someone is making a change, to really know what's the impact, it had to be tested in production. And that makes everyone hard. Like we don't, it lowers the velocity, puts more questions in the queue. Like, have you made sure everything is right for this? And this sort of thing steered me to what I'm doing now. Like to sort of, as of last 2 weeks, I joined ParadeDB, and the promise here is that it's a transactional Elasticsearch alternative. So we ship a Postgres extension that is built on Tantivy, which is a Rust fork of Lucene. And it uses Postgres storage. And that's my personal sort of observation, is that if I have to rebuild the Instacart-like search, it will be like a ParadeDB. A lot of things would be, especially the DevX, it would be like much simple. And yesterday I saw there's just steering the conversation in different ways. Yesterday I saw a blog post by Target. They moved their search workload to LOIDB in a sort of a Postgres compatible way. And it's not clear what were their motivations. There could be similar motivations, but their outcomes are very similar. Like, the relevance is better because they could join more things in the database. They also saw the cost of the normalized data reduced. So that's pretty much matching with what we saw at Instacart.
Nice. Very, very cool. Well, Ankit, it was amazing to have you on the show. We appreciate kind of the total Postgres, Instacart kind of deep dive. We'll follow your work at ParadeDB. We're excited about all of that. Thank you for being on the show.
It is an honor. Thank you.
Thank you.
The Data Engineering Show is brought to you by Firebolt, the cloud data warehouse for AI apps and low latency analytics. Get your free credits and start your trial at firebolt.io.